Good morning from sunny California, Southern California. And my name is Djokic, just the way it's spelled. You shouldn't have a problem reading this. I am a principal consultant at Esri. What that means is I have a lot of gray hair and I focus on water resources. So what I'll talk to you this morning is, this afternoon, is about hydrographic feature extraction from digital elevation models. And actually, Lenka's presentation was awesome. It really set up a lot of things, although I didn't understand quite a bit. But let me get into that and see if we can get some time back here. So really what we want to do here, or I'd like to do here, is talk about the ability to extract hydrographic features from the elevation models. So we have a lot of data basically across the world, but definitely in US, that are digital elevation models that are derived from either LiDAR or IFSAR sensors, resolution that can go into sub-meter resolution. So your cell sizes are sub-meter. These are flown across the whole country. The whole country of US is about 200 times larger area-wise than Slovakia. So we have a lot of data to process. And there is a national program called 3DHP, or 3D as in terrain, derived hydrography. And our motto with that is to see if we can do better, faster, cheaper, and process the country. Right now, the plan to do this is something in the range of 8 years. And it's led by our US Geological Survey. So the idea here is that can we derive the blue lines, or as I like to call them, the blue blobs. So not only the hydrography that we have here, so streams, but also lakes, wetlands, depressions, and everything else. And as we go through this, I'll show you something that I call a picture book. Remember, kind of this image will go through this, and pay special attention to these areas here where the streams cross the built infrastructure, the roads. So there are some culverts and bridges here, here, and here, and a few other places. So pay attention to those. So what do we want to do here? There are many different techniques. There are no standardized approaches to do this. And what we would like to do is ability to actually do something that's consistent, and that with consistent techniques and methodologies, we can produce consistent data. So do science if we can, and in the process minimize human intervention. So we want to minimize any work by hand. And I, as a tool developer, want to be able to build tools, as I like to call it, an efficient super button that you can, as much as possible, push it, go have a cup of coffee or lunch, come back, things are done, and you just have to quality control and maybe refine the stuff. So, sorry about that. Before we go into gory details, are we really talking about science or some magic? And what we are really trying to do here is the term of alchemy was to start with lead and ore and try to derive some gold, and from that maybe even some cool gold products. So if we apply the same principle and we think about that in the context of what we are trying to do with our elevation models, what we are really trying to do is come up with a surface which we know is not perfect, but it has a lot of noise and artifacts, both of processing and data collection. And from that, we want to extract our hydrographic features. And not only that, but we want to do some highly focused derivatives in water, like a rating curve, how much water can flow through a stream from a pretty noisy data set. So are we trying to do science or magic? So hopefully more science and less magic. The tools that I'll talk about are all available in Archidra. Archidra is basically started as a data model, lots of tools, about 250 of them. We have many, many workflows in different areas of water resources, and a community through which we share experiences, ideas, data, methodologies, documentation, etc. Archidra is free. Of course, you have to have our technology. So as there is ArcGIS, either ArcMap or Pro, and you can just download, use it, and it's pretty much open source. So all the code is available to you. Most of it is written in Python and using ArcPy for those of you who use our technology. There are lots and lots and lots of tools in Archidra. We have about 250 different tools, and we'll be really talking about tools that are kind of in this domain of terrain processing, but there is a lots of capabilities built into this. I will show you a couple of things here, two different techniques, what I call the classic, and also some of the AI techniques, machine learning techniques for feature extraction. The classic techniques, we are going to talk about two of them. The traditional one, in which we first fill the depressions, we identified the flow direction, flow accumulation, and then from that stream definition. And there is a new technique that's available in Pro 3.0 and up. We call it a continuous flow technique, which really looks at the least cost path of traversing the surface. And so you can fall into a depression, look around the depression, find the least cost to get out of the depression, and then keep flowing through the terrain. And there are also many other techniques that you can use to pre-process the terrain, to filter it, to maybe smooth it, and make this analysis a little bit smoother. Of course, it's not that simple when you start looking at depressions and things. Each of these steps is much richer. We are looking at probably around 25, 30 different individual steps in this process of coming from the raw elevation model to a final product. Another technique that I'll briefly mention are some of the machine learning techniques in which you take different inputs. We'll focus on the elevation, but it can be multiple sources. From them, you derive hydrography indicators. So these are different geomorphologic indicators that are surrogates for water, where the water would want to concentrate. And we then use the observed hydrography known locations. We can train the model. Once you have the model trained, you can apply it to other areas and predict where hydrography should be. So I'm going to show you, all right. So I'm going to show you what I call the picture book, a lot of results based on a very small area, about 6,000 by 6,000 cells. These are 0.6 meter cell size, digital elevation model. And this is the I like to call it dirt, right? The terrain. And these are the hydrologist approved blue lines for this area. So somebody went and refined and looked at those and manually fixed them and made them flow the way a hydrologist would interpret this terrain. And so again, pay special attention to these areas where the water crosses the man-made structures, and how our automated system do or do not capture that crossing. So let's look at the traditional, the classic way where we first filled the DEM. We used full resolution of the DEM, and you can see these yellow lines represent the synthetic streams automatically derived from the digital elevation using the fill technique. In the areas where there is a well-defined topography, it matches pretty well with the true blue lines, but as soon as you fall into the flat areas, it kind of goes a little bit crazy. The culverts, this one we get lucky. Looks okay here, but the other culverts and bridges are not well represented, especially like this area here. You can see that it completely misses and pushes the water to flow along the road instead of finding the path through these openings in the embankments and ability to cut across. So let's look at this new technique. So this is the continuous flow approach, in which we do not fill, and you can see that there is a much, much better representation and match with the true blue lines. So this strange looking linear features that are artifact of filling the depressions before you find the flow direction are pretty much gone. The fit in the steeper area is really good. In flat area is pretty decent, but again, it does not really capture the man-made structures. And so it's definitely an improvement, but it's not perfection yet. Another technique that I want to show you here. So this is the continuous flow technique with smoothing of the terrain, which theoretically should improve the fit. And in some areas, you can argue, like here, we are now cutting across the DM instead of flowing along, but still not capturing properly the man-made structures. But in some areas, this smoothing, although you expect it to be better, is introducing some really strange artifacts. And the final example that I wanted to show you on the classic technique is really coarseness of the digital elevation model, basically saying, can we just look at the density? Maybe the digital elevation model is too good for what we are trying to do. And if we use not smoothing, but coarser representation, can we maybe get better results? I don't know that we can get better results, but what is interesting here is we are using a 5 times coarser resolution. And the results are not that dramatically worse. So this is food for thought, right? Where maybe we really don't need to do such a high resolution to get decent results. Let's now quickly look at some of the machine learning techniques. This is really using the random trees, so it's not a deep learning, it's just a machine learning technique. The upper part was used for training, and the lower part for prediction. So I'm going to show you now the zoomed in area. So if you can see slight red dots, this is the calibrated points, which in this area you would expect to match well, because that was used for training. While in here, prediction, you can see some resemblance, but we are missing a lot of information here. And so this is the 50% probability hit. So if we reduce this probability and we increase it to 25 and 10%, you can see a much better showing of these linear elements, but we can see kind of a mask developing, but not quite the detail that we are looking for. And then if we go and again use coarser DMs to do a similar activity, you can again see a pattern, but it's not a great one. And if you look in the context of hill shade, you can see that some of these areas are well captured, but we are still not getting the man-made features. So this is what is a real problem, right? We need specific elements that will separately identify where man-made structures are and enforce those into our network and make sure that our hydrography follows that. So we're working on some other deep learning techniques which are more conducive to identifying linear features in a system. The random trees don't quite do that, so that this is work in progress. With all the machine learning techniques, not only do you need to know your hydrology and morphology, but you now also need to know how to do the machine learning and its statistics. So as they say, bigger lie statistics, right? So you need to know a lot of detail about different techniques before you can actually get good things. Neither classic nor machine learning technique really is perfect, but that's not surprising. So this is work in progress. There are a lot of things that we still need to work on and figure out. And I think with that, I will stop here and I will leave you with a couple of favorite quotes of mine and take some questions.